Based learning, network analysis, power factor correction. To apply related principles or methods as learned in network analysis based on the task. To understand the principles of power factor correction in AC circuit while demonstrating the concept of network analysis. Able to construct a circuit and calculate the value of power factor based on given information. Apply and show various methods to solve the problem given.
Concept to analyze AC circuit. First step, understand and draw the circuit based on the information given. Second step, mathematically analyze the circuit, solving for all voltage and current values using Ohm's law. Third step, find the real and reactive power losses and calculate the power factor. Finally, draw the power triangle. Fourth step, calculate the value of power factor by doing power factor correction and draw the power triangle before and after POF to analyze the differences.
Power factor correction are used to give benefits to electric power systems. Cost or bill reductions. High voltage support. Improve stability and efficiency of the network. Reduced transmission losses. Power factor correction brings the power factor of an AC power circuit closer to unity, which is one method in analyzing AC circuit before and after power factor correction. There are big differences in terms of step.
This is the example of power triangle that shows real power, reactive power. Apparent power equals sum of real and reactive power. We will compare both power triangle before and after PFC by drawing. By doing PFC, it will eliminate the charges related to reactive power consumption. If the utility is adding a power factor penalty or billing for apparent power, kVA, there will be reduction in reactive power.
So, after done all the calculation, we will go through the simulation. We use Multisim software as medium. We have to perform AC power analysis. First of all, configure all the circuit as drawn during the calculation. Make sure all the components are placed properly. Second, measure the first parameter, which is current in each load and total current. Place all the current probe at each load. First is probe 1. Second is probe 2. Third is probe 3. Fourth is probe 4. Fifth is probe 5. Sixth is probe 6. And then hover to simulate, which is using single frequency AC, set the frequency to 50 Hz, complex number format, which is magnitude and phase, and add all variables, probe, and click run. Third is to measure the real and reactive power losses at the transmission line. We already place current probe. Now place differential voltage probe at each transmission line. First, voltage probe 2. Second, voltage probe 4. Third, voltage probe 6. And then click single frequency AC, change the complex form to real and imaginary. At the variables, we have to add expression. V multiply with conjugate I for each transmission line. Lastly, click run and we will get the result.
Fourth, we would like to compare the value of power factor after the power factor correction. So, in order to measure value of power factor correction. Step 1, place the wattmeter at voltage supply. Step 2, parallel the capacitor at any branch. Step 3, run interactive simulation. As you can see, the value of power factor is 0.98, similar with the requested value by the question. This shows that capacitor improved the power factor.
First of all, we look at the circuit's parameter and configuration, where we use the default value of the equation, where we are from group 1. It's the task 1 that we need to find from the circuit given to us. The calculation at load 3 and line transmission 3 to 4. Firstly, start to find the angle by using power factor formula, which is tangent theta equal to Q over P. We calculate the value of complex power using power factor formula, which is cos theta equal to P over S. We find the value of impedance at the load 3 by using given voltage, which is 240 angle 12 volt. In formula S equal to V square over Z, we find the current at the load 3 by using Ohm's law between given voltage impedance at load 3. Next, we find the total impedance at the line transmission 3 to 4 and load 3. By summing up both, we find the voltage at line transmission 3-4, where we use Ohm's law, V equal to Iz. Then we got the voltage at line transmission 3-4, which is 0.3236 angle 46.51 volt. Next, we find the total voltage at the line transmission 3 and 4 and load 3 by using Ohm's law between current at load 3 and total impedance at line transmission 3, 4 and load 3. The formula is V equal to Iz. Next, we proceed to step 2, calculation at load 2 and line transmission 2 to 3. First of all, we start to find the angle using power factor formula. We can find the complex power by using cos theta equal to P over S. After we got the value of apparent power, we find the impedance at load 2, where S equal to V square over Z conjugate. We find the current at the load 2 using Ohm's law between total voltage and line transmission 3 to 4 and load 3 and impedance at load 2. Next, we calculate current at the transmission 2 to 3, where we summing up the current at the load 2 and the current at line transmission 3-4. After that, we find the voltage at transmission 2-3 using Ohm's law between current at transmission 2-3 and impedance at line transmission 2 to 3, where we use formula V equal to Iz, where we use I at line 2-3 multiply impedance at line 2 to 3. Next, we find the total voltage for load 1 by summing up voltage at transmission 2 to 3 and voltage at load 2. Proceed for calculation at load 1. The calculation at load 1 and line transmission 1 to 2. Firstly, we start to find the angle using power factor formula. We find the complex power by using power factor formula. Here we got the value of complex power. We find the impedance at load 1 by using S equal to V square over Z conjugate. Then we got Z at load 1 is 6.6561 angle 23.07 ohms. Then we find the current at load 1 using Ohm's law between total voltage at line transmission 2 to 3 and load 2 and impedance at load 2. Next, we calculate the current at transmission 1 to 2 by summing up with current at transmission 2 to 3 and current at load 1. We find the voltage at transmission 1 to 2 using Ohm's law between current at transmission 1 to 2 and impedance at the line transmission 1 to 2. After that, we find the total voltage supply by summing up voltage at the transmission 1 to 2 and voltage at load 1. Next, we calculate the parallel impedance. In this case, we need to find the total current. So we start with calculate the impedance from load 3 until load 1. So we can use voltage divider rule. We calculate the parallel impedance between impedance at line transmission 3 to 4 and load 3, impedance at line transmission 2 to 3 and load 2, and impedance at load 1. Then we got the Z parallel, which is 1.773 plus J 0.411. Next, we proceed by applying VDR, which is voltage divider rule, to find the voltage at transmission 1 to 2. Then we calculate total current supply by using Ohm's law between voltage at transmission 1 to 2 and impedance at line transmission 1 to 2. Finally, we calculate the total impedance by using Ohm's law between total voltage supply and current supply, where Z total equal to voltage supply divided by current supply. We proceed to step 4, calculation real and reactive power losses at transmission line. First of all, we calculate the complex power at line transmission 3 to 4 by using formula S equal to VI conjugate, where V is voltage at line transmission 3 to 4 and I is the current at the line transmission 3 to 4 and load 3. Then we calculate the complex power at line transmission 2 to 3 by using the same formula. Next, we calculate the complex power at line transmission 1 to 2 by using same formula. Step 5, we need to find the total apparent power, real power and reactive power of the system. We calculate the complex power of system by using S equal to VI conjugate, where V is total voltage supply and I is total current supply. Next, we need to draw the complete power triangle. We draw the positive power triangle because of connected with inductive loads and the system lagging by 11.4, and the power factor we got is 0.98027 task 2 to do power factor correction. In this case, however, since there is just slightly difference the angle power factor that need to be improved, and the power factor we got from calculation, so we decided to improve the system by using 0.98 leading. Okay, first of all, we start to find the new angle using power factor formula and calculate the complex power using the same angle and the same value of active power. We calculate the reactive power by using the power factor formula. We draw the power triangle before and the power triangle after power factor correction to calculate the new reactive power, which is Q, to be added in the system. Because of the old one is on top, so they need to go down, so it need to add capacitor QC equal to V square over at C. Lastly, we calculate the value of capacitor used to be added in the system for power factor correction.
As we know, power factor correction brings the power factor of an AC power circuit closer to unity, which is won by supplying reactive power of opposite sign, adding capacitors or inductors that act to cancel the inductive or capacitive effects of the load, respectively. There are few applications on power factor correction where, for power factor correction of high voltage power systems or large industrial loads, power electronic devices such as the static VAR compensator or STATCOM are increasingly used. These systems are able to compensate sudden changes of power factor much more rapidly than contactor-switched capacitor banks, and being solid-state require less maintenance than synchronous condensers.